Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section, we're going to cover the topic of arc lengths in parametric coordinates, or in parametric equations, okay? So let's stop and think about where we've been and where we're going, because it helps to get the big picture. A few sections ago, we talked about the topic of arc length, which was just telling you how to integrate a function so that you can actually find the length of that function. And then we found an equation that talked about the surface area of a function that's been rotated about the x-axis, and that also involved arc lengths, and using that we kind of built on that to find a relation there. Then we switched gears and talked about how to write functions in terms of parametric equations, which are just equations for x and for y separately in terms of a third variable usually called t. T for time, okay? So you have an equation for x and an equation for y. We talked about that. Now this section is going to be the arc length formula in terms of parametric equations. So this section exactly mirrors the section on arc length. So go back there and read that and understand that if you have already watched it. But this is doing exactly what that function does, and exactly what that section does, except the equations here are going to apply to systems that are defined in parametric equations. So the concept is the same. Finding the length of an arc is exactly what we're going to do. It's just that now the equations are not f of x, they're x of t and y of t. Parametric equations, okay? So recall that we found a function in Cartesian coordinates. The length, the arc length of that function was an integral from a to b, okay, of the square root of 1 plus f prime of x, which is the derivative of x squared, dx. That's what we found before. We take our function of x, we take the derivative, we square it, we put it in here, we integrate from a to b along x, and that is the length of that function. Now we want to find an equivalent expression in terms of parametric equations where you don't have f of x, you have x of t, some variable t, and y of t. So obviously this thing's going to look a little bit different, but once we know what it looks like, it's going to be applied exactly the same way to find the arc length. We're just going to plug it in there and do the integrals, okay? So this can also be written as the integral of a to b, just to kind of make it clear, the square root of 1 plus df or dy dx squared. Same thing. dy dx, f prime of x is really the same thing, dx. Okay? All right. Now, what we want to do is we want to find an equivalent expression, okay, when the function is not given in terms of f of x, it's given in terms of x of t and y of t. Or it could be any variable here, but we usually call t. So what we're going to have is, draw a little picture, okay? What we're going to have is, we're going to have some function. Let's say it goes up like this and it goes down, whatever this function looks like, okay? This is x and this is y, okay? And we want to find the length of this function, and if this function were f of x and defined in terms of an f of x, we would simply put it in here and get the answer. But let's say this function is not defined in terms of f of x. It has x of t, defining the x-coordinate, and y of t defining the y-coordinate, just as we talked in the last section on parametric equations, okay? So we want to find the arc length, okay? So what we're going to do is we're going to do something very similar to what we did before when we derived the arc length the first place. We're going to look at 2 points, okay? And this point is going to be called P, and I'm going to call him P sub I, just because he's the ith point along here. And this point, which is very close, but not quite on top of him, he's going to be called P sub I minus 1. And all that means is, this is fancy calculus notation that you see in your books. Okay, all this means is here's a point. I call it the ith point because he's just a point in the middle somewhere. I don't know what number he is. He's just got some little letter that means he's the ith point. And the point right before him is just I minus 1. It's just another label, just so I can keep these points different because I'm going to derive something down below. I don't want to get them confused, okay? Now, just like we did before, what we're going to be looking at is the little tiny arc between them, the distance, the straight line distance between them, because we're going to end up deriving this arc length formula, and that's exactly how we did it way back then. We looked at the distance between 2 points, the straight line distance, and then we just sort of went from there and derived that arc length formula. Okay, so the distance, beginning here, the distance between P sub I minus 1 and P sub I, the straight line distance, okay, is given by the following. Here's the distance from P sub I minus 1 to p sub I, that's all this little bracket means, it's just the distance between them, is equal to the square root, just as if we did it before back in the arc length section, of delta x sub I squared plus delta y sub I squared. Okay? All we're saying here is, okay, this p, this point, has an x and a y value, and this point has an x and a y value. This is the distance formula. That's all it is. I'm looking at the difference in the x coordinates, and I'm squaring it, and I'm looking at the difference in the y coordinates, and I'm squaring them. Okay, the little sub I just means I'm doing it here at the ith and the ith minus 1 point. That's all that means. But I'm looking at the difference in the x's and the difference in the y's, and I'm squaring it. I'm taking the square root, and that is the actual distance of this line segment. It's not the true distance along the curve. It's the distance between this line segment if I were to draw a straight line between those 2 points, which is what I've done. Okay, now the next step is crucial for you to understand, so I'm going to spend a fair amount of time on this. I'm going to go ahead and write it down, and then we're going to talk about it. I can rewrite this as follows. This can be written as the square root. I'm going to rewrite delta x here as, it's going to be written as df dt, okay, times delta t squared. I'm going to go ahead and continue on, and then we're going to come back to it. So I'm going to put some parentheses here. It's going to help us, okay? Plus another bracket, plus dg dt, and I'll tell you what these mean here in just a second, times delta t, okay, again squared. And I'm taking the square root. So you see what I've done is I've written delta x as this stuff here because I'm still squaring it and I'm still squaring this. And I'm doing that. Now, first I need to explain a few things. What are f and what are g, okay? Up here, when I said I had x as a function of t, what I really should have written is I'm defining some function f is equal to x of t, and I'm defining some function g as y sub t. So really all I'm doing here is I'm saying that f is the function in terms of the function that governs x, and g is the function that governs y, okay? So going back down here, look at what I'm doing. I'm trying to find an expression for delta x. That's how far I've moved in this direction, okay? But you see, x is in terms of this function here, which I've labeled f. So if I take the derivative of f with respect to t, that variable that it depends on, because f is a function of t, okay? If I take the derivative of f with respect to t, but then multiply by delta t, whatever that is, what I'm going to get is delta x. And you can just kind of look at the cancellation here. The delta t would cancel with the delta t, leaving me with df, which since f is equal to x of t, that's the same thing as what I have up here. So this is exactly the same as what I talked about in the arc length section. If you have miles per hour, okay, that's sort of a rate of change or a slope. Okay, this is the ratio of how far I go to how long it takes, and I multiply by the number of hours it takes. Then what I'm going to have in the end is how far I've gone, miles, because the hours cancel here. So what I have here is df dt is the rate of change of this function f, and f is how x behaves. So what I'm doing is I'm taking the derivative of how x changes with respect to time, but I multiply by what time is, how long I'm actually looking at this. So it's sort of the same thing as this. So what I end up with is what df is, and since that's what x is, it's just what delta x is. So doing this, looking at the rate of change times the time, I'm finding out how far x has moved, and I'm doing exactly the same here for y. dg dt, okay, g is just another label that means he's talking about y. Okay, g is equal to y of t, so when I take the derivative of g, I'm looking at how y changes with respect to time, but then I multiply by the actual length of time that I'm looking at this thing. So it's kind of like the miles per hour times the hours. I'm left with, in this case the miles, I'm left with something that talks about g, and g is what y is. So I end up getting my delta y. So these are fancy ways to rewrite delta x and delta y. We're looking at the rate of change of how x changes, looking at the length of time, and the rate of change of how y changes, multiply by the length of time. So I'm getting the total amount that x changes here, and I'm getting the total amount that y changes here, and that's what these quantities are, okay? So I'm just rewriting it, that's all I'm doing. Okay, but it is a very, very important step. Now, what can I do next? Okay, what can I do next? Everything is squared here, so if I use and kind of distribute the square in, I'm going to have df dt squared, delta t squared, dg dt squared, and delta t squared. So in the end, if I do all of that, I'm going to have some delta t squareds running around. So what I'm going to do is I'm going to keep them under the radical for now, but I'm going to have delta t squared, okay? I'm going to have delta t squared. And on the inside, okay, I'm still going to have df dt squared plus dg dt squared, okay? And I'm going to have a bracket right here, okay? So I'm going to have that there. Now look, this is a quantity altogether, and this is a quantity off by himself. I can take the square root of this square here, and delta t can come right on out. So let's go over here, and let's continue simplifying. Okay, what I would have here then, on the inside, is I would simply have my df dt squared plus dg dt squared, and that delta t that was in here squared, I'm going to square root him, I'm going to take that delta t, I'm going to put him at the end, delta t. Okay, so what have we found? This is a form of an equation that talks about the length between the segment between those 2 points right here, between p and pi and pi minus 1. This is just the length here between these 2 points, and if this equation was written in parametric form, where the x-coordinate was a function f and the y-coordinate was a function g. That's all it's saying. So I have some derivatives over there. That's all that's going on. Now, if I want to find the arc length of the whole thing, I need to somehow add up all these little segments, but at the same time, I need to shrink these segments down to 0. So this quantity times a delta is going to turn into an integral, and that delta t is going to turn into a differential dt. That's what the integration process does. So I'm integrating from alpha to beta, and I'll explain what alpha and beta are in a second. Okay, the square root of df, well, it's going to be df dt and dg dt, but since f is equal to x, now we can just go back and say it's going to be dx dt squared plus dy dt squared dt. That's what the integration process does. When you look at adding up all of those little segments, and you make those segments approach 0 so they become a differential, and you sum over them, it becomes a dt in calculus notation. So here's what you have. This is the arc length formula, okay? I could have just written it on the board and told you to memorize it, but I wanted to try to show you where it comes from, and it comes directly from the arc length formula that you already know. It just looks a whole lot different. So parametric equations have a function x of t, okay, and a function y of t. All you have to do is take the derivatives of those, square them, put them in here, and integrate, and you get the answer. Now, what is alpha and beta? Those are just the limits in terms of t. You see, you always have to have some limits to integrate over. In the original arc length section, we had a and b. Now, I'm trying to keep it different from that section, so most books will not use a and b just to keep the confusion to a minimum. They'll use alpha and beta. It's just the limits of integration, the limits over this t, okay? Okay, so let's just review really quickly. The original arc length formula was given by this, okay? And basically we said we had an equation that had a parametric representation, x of t and y of t, and we just put the label that x of t was f and y of t was g. The reason we did that is because if we started using x of t and y of t all through here, you might get confused between this delta x and x of t, and there'll be too many x's running around. So we say f is x of t and g is y of t. Now the distance between any two arbitrary points is what the distance formula is, just the difference in x squared, the difference in y squared. And then we just wanted to write what that is. So the magic of the whole thing was knowing that delta x, which is this distance here, was how the rate of change of f, which is x, the rate of change of f with time times the time that it took to move between those 2 points, okay? And then the same thing with y. And then we just factored out delta t squared, took the square root of it, moved it outside the integral, and what we had left on the inside was just the df dt and dg dt. And then when we were finally done, we did our integration, we turned the delta t into a dt, we took our limits of integration to be whatever the problem is going to end up saying. It's going to be a limits in terms of time, t, and then we just turn these f's and g's back into x's and y's, because usually the parametric equations are given in terms of x of t and y of t there. So this is what you need to know. We're going to work some problems to show you how to use it. Okay, now the first example is x is equal to 1 plus 2 times the sine of pi t, okay, that's the x coordinate, and y is equal to 3 minus 2 times cosine of pi t, okay, and t in this case runs from 0 to 1. So don't forget what you're doing. You have a parametric equation. Now all that means is x is defined in terms of some variable t, which is time. Y is defined in terms of time. And as time marches on between 0 and 1 second, let's say, you plot your xy points and you're carving a curve out. That's all you're doing. It's just that it's in terms of parametric form instead of the f of x form that you've used so far. So the arc length formula, the length between of that function between the starting and the ending point is the integration of alpha to beta, which are just the endpoints in time, of the square root of dx dt squared plus dy dt squared dt. Okay, that's all we're doing. Okay, so obviously we have to find dx dt and dy dt, so let's do that right now, and then we'll go ahead and plug it in there, and we will solve it. Okay, so dx dt is equal to derivative of this. What is that going to be? Derivative of 1 is 0. Moving on to here, it's going to be 2 times derivative of sine is cosine of pi t times the derivative of the inside. Derivative of pi t is just going to be pi. Okay, so the derivative here is 2 pi times the cosine of pi t. 2 pi times cosine pi t. Okay, now dx dt squared, which is what we're going to need to put in here, is going to be equal to 4 pi squared times cosine squared of pi t. All we did was square it. That's all we did. Okay, now dy dt is going to be equal to, looking up here, derivative of 3 is 0. Looking here, negative 2 times derivative of cosine is negative sine of pi t, okay, times the derivative of the inside, which again is pi. So negative times negative gives us positive 2 pi times the sine of pi t. So that's the derivative, 2 pi times the sine of pi t, and then dy dx squared, we're going to square this, is going to be 4 pi squared times sine squared of pi t. Okay, so now we found the derivative of x, the derivative of y, and we found the square of both of those terms. So let's go ahead and put it into the arc length formula and see what we have. Arc length is going to equal integral from alpha to Bravo. Alpha is 0 and b is 1. So 0 to 1 of the square root of dx dt squared, which we found right here, which was 4 pi squared times cosine squared of pi t, plus dy dt squared, which we found right here, which is 4 pi squared times the sine squared of pi t. And we're integrating over dt. Okay? So that's what we have. It looks kind of ugly, but I think you'll see that it reduces nicely. Integral 0 to 1 square root. Now what can we do inside here? I've got a 4 pi squared common and a 4 pi squared, so I'm going to factor that out. It's going to be 4 pi squared, and on the inside I'm just going to have this plus this, which is going to be cosine squared of pi t, okay, plus sine squared of pi t, okay, dt, okay. So all I've done here, is I factored out the 4 pi squared, okay. So you see the reason I did that is because I have a 4 pi squared here. I can take the square root of this and pull him outside the integral, and then I'm going to have some stuff left on the inside, okay. So let's do that right here. That's going to be equal to square root of 4 pi squared is just going to be 2 pi, right? So it's going to be 2 times pi times the integral from 0 to 1. Now look at what I have here. I pulled out this, okay, now look at what I have left. Cosine pi squared, or cosine squared of something, plus sine squared of something. Remember that identity, the universal identity of trig. Cosine squared of any argument plus sine squared of that same argument is 1. Cosine squared plus sine squared is 1. If the arguments are the same, this is always going to equal 1. No matter what value of t I put in here, it's always going to equal 1. So this whole entire thing is 1. So if I pull out the 4 pi squared, all I'm going to have is square root of 1 dt. Okay? Which, you know, this is just going to become 1. So all you're going to have in the end is the length is going to be equal to 2 times pi times the integral from 0 to 1 of dt, because that square root of 1 is just equal to 1. So when you take the integral of this, it's obviously going to be equal to 2 pi t evaluated from 0 to 1. Okay? And that's just going to be equal to 2 pi, and then evaluating at 1, t is, plugging into t is 1 minus 0, plugging into 0, so you're just going to have 2 pi. Okay, and that's going to be the answer. It's 2 pi. So let's review what we've done. We had a parametric form of some curve, okay, and we're trying to find the length of that. And we know that it goes between, time marches on between 0 and 1, could be seconds, could be milliseconds, whatever. This is the equation that we derived for the arc length of a function in parametric coordinates. We found out what dx dt was equal to, and we squared it. We found out what dy dt was equal to, and we squared it, and then we plugged it into here. And we noticed right away we had a 4 pi squared common, so we factored it out, keeping it under the radical, and all we had left was this cosine squared plus sine squared. Okay? When we pulled this out of the radical, it came outside the integral as 2 pi, because we take the square root, and all that was left was cosine squared plus sine squared, which is always equal to 1. So we had square root of 1 in the inside, which obviously is equal to just 1. So we had 2 pi times the integral of 1 dt, which is just 2 pi t, and then plugging in, we got the answer there is 2 pi. So that is the length of that arc that was defined in parametric coordinates. Okay, now the next problem is going to be x is equal to 5t squared plus 1, and y is going to be equal to 4 minus 3t squared. And this parametric equation set is only going to run from 0 to 2. Time goes from 0 to 2 seconds, let's say. Okay, so obviously we want to apply the equation that we know, which is the arc length, which is what we're trying to find, is an integral from alpha to bravo, which is just the endpoints here, of the square root of dx dt squared plus dy dt squared. Okay, and we're integrating over dt. Okay, so obviously we need to find dx dt and dy dt, and we need to find their squares. So dx dt is equal to, looking back up here, it's going to be 2 times 5 is 10t to the first power for dx dt. Okay, and that would mean that dx dt squared is equal to 10 times 10 is 100 t squared. Okay, now dy dt is equal to derivative of this, derivative of 4 is 0, derivative of this, 2 times negative 3 is negative 6t to the first power, okay? And then dy dt squared, which is what we need to know to put into here, is negative 6 times negative 6 is positive 36t squared. So these are important things. We know what those quantities are, and let's go ahead and plug them in and see what we have. The length is going to be the integral from 0 to 2, because that's alpha and beta, okay, of dx dt squared, which is 100, well actually it's the square root of 100t squared plus 36t squared, because that's dy dt squared, and we're integrating over dt. Okay, now you have 100t squared plus 36t squared, so you can add those up. 0 to 2, square root of 136t squared dt. Okay, now this is just a number here times t squared. So I can take the square root of 136 and I can take the square root of t squared. Okay, so what I'm going to have is I'm going to have the square root of 136, okay, times the integral of 0 to 2. And on the inside I'm going to have square root of t squared, which is just t dt. You see, all I did was I took the square root of the 136, I moved it out of the integral, I left it alone because I don't know how to take the square root of that yet. Okay, and the root of t squared is just t, so that's what's left on the inside. And so I'm going to have root of 136, okay, over 2 t squared, actually taking the integral of this thing, because it's this over exponent plus 1, and then t to the exponent plus 1, okay? And I'm evaluating this from 0 to 2, okay? I'm evaluating that from 0 to 2. So what I'm going to have then is I'm going to have root 136 over 2, and evaluating at 2, 2 squared is going to be 4, minus 0 squared, which is just 0. So I'm going to have a nice little cancellation here. I'm going to get rid of this 2 on the bottom. So I'm going to have, basically in the end, I'm going to have 2 times the square root of 136, because 4 divided by 2 is 2, and then you get that. So let's see if we can simplify this any further, and we'll just move right on over here. 2 times the square root of 136. Well, let's see if we can simplify that. What times what will give me 136? Well, 2 times 68 actually gives you 136, and then 68 is 2 times 34. Okay, so this radical is 2 times 2 times 134. So when you're doing radicals, you all know that you're just looking for pairs, and so we did find a pair of 2's. So this thing is actually equal to this 2 times this 2 that comes out of the radical times the square root of 34. So the answer is just going to be equal to 4 times the square root of 34. And that is the answer, 4 times the square root of 34. So just reviewing the bitting again, here's our parametric equations. We took the derivatives and squared them. We took the derivative of y and squared it. We put them under the radical. We were able to add them. Take the square root, pull out the square root of 136. Root of t squared just gave us this. Integrated became a root 136 over 2 t squared, evaluated from 0 to 2, and it just became a simple matter of simplifying that. So this section dealt with arc length and parametric equations. When a function is defined in parametric terms, when it has x of t and y of t, you have a different arc length formula to use. But it's really not that hard. You take the derivatives, you square them, you put it into the formula, the relation that we talked about, and you crank through the integral. Usually you'll get some kind of nice simplification under that radical, so you can take the square root of it and make it integrable, and without too many sessions of banging your head against the wall. And that's how you tackle arc length and parametric equations.